All right. So we are talking about actuated signal, and this is related to one of your homework problems, one of the only ones that you should still be working on that we haven't yet covered. And you will see that even in this problem, we are going to look at a lot of different aspects of what we talked about before in terms of desirable cycle length, in terms of sum of critical lane volumes. So all of those things will still come into the picture here, but some additional aspects of detection that provide the flexibility for the traffic signal operations. And obviously there's going to be pedestrian and all of that, all of those things would be there. So let's think about this. So let's kind of go back to this actuated signal chapter. And then we've already talked about the different types of actuated controls. One thing I want to first highlight from this chapter is if you go to section 20.3 on page 568. We go to page 568 here. So first of all, the actuated signal controller is manufactured in one of the two standards, basically NEMA standards. That is the most, that remains sort of the standard, like that we use. The NEMA standards specify all the features. They do constant updating of those standards, and that's basically how we design controllers, all the sort of the electronics of it, all the electric features, and all that. And then there is this firmware, built-in features of the hardware and how the timing software interacts with it. And there's another type, type 170. So that's another one that could be modified. But I think for the most part, the most signal controllers you'll find, they will be sort of NEMA controller. So that's one thing I wanted to point out. And then these are the important features of the actuated signal control. This is 20.3.1. This is the minimum green time. Capital G minimum. Each actuated phase has a minimum green time, right? So that means once the signal turns green, it will remain green for at least a certain amount of time. And that number is specified at the signal controller level. Okay, so we always specify that. So that's your minimum green time. The smallest amount of green time that has to be allocated to each phase. Once you give it green, and always we measure that in seconds, so that S is for seconds. Then you have what we call the unit or vehicle extension. And maybe you have observed this when you're driving around at an intersection approach. If you are too far from the vehicle that's ahead of you, a lot of times light will turn yellow. And again, I'm not sort of telling you to encourage any kind of unsafe behavior or anything like that. But if you are sort of, the closer you are to the vehicle that's ahead of you, the chances of light turning yellow would be reduced. And why would that happen? Because every controller has what we call the unit extension. So a unit extension has three purposes. It represents the maximum gap between actuations. Actuations means a detection of a vehicle that leads to the green signal. It represents the maximum gap between actuation as the single detector required to retain the green. What does that mean? That basically the detectors get actuated by a vehicle passing over them, or if you have a camera-based detection, if a vehicle appears in frame, right? So if there is a vehicle appearing in frame, it leaves the frame, and the next vehicle doesn't appear into the frame until the unit extension is passed. That means the detector thinks that there is not enough demand coming in. It's time to turn that signal yellow, that signal approach to be yellow. Okay, so that's what it does. It is also the amount of time added to the green phase with additional actuator. But if it does see another vehicle coming in, it adds a certain amount of another unit extension to the mix. Okay, it will add another unit extension to that phase. Okay, so then your signal, phasing for that movement will get longer, a little bit longer. And then the last one, that unit extension must be of sufficient length to allow a vehicle to travel from the detector to the stop line. Now remember, our detectors typically, there are cases where the detectors are not located right at the stop line. Okay, we'll talk about those cases. But it's very important to know that our detector may or may not be located right at the stop line. Okay, and anytime we provide this unit or vehicle extension, the time that you're extending the green to, the vehicle must be able to travel from the detector to the stop line. Right, so that time should be enough. So we always check for that level of timing. Yes.
This is so then like the vehicle is between the detector and the light, it just doesn't switch.
It doesn't switch light. It doesn't turn yellow by that time. So it has to reach the stop line so that when it turns yellow, at least they have the opportunity of entering the intersection on yellow and move on. And again, this might be, you can make it a little bit more conservative if you don't want vehicles to be entering on yellow. If you only want them entering to be on green, you could extend that time a little bit more. Okay, again, that's what I mean by there is going to be always some variation of how agencies and jurisdiction use these things. And then there is called the maximum green time. Each phase has a maximum green time. That limits the time of the green phase. And now, we always specify that maximum green time. You might think that, if you have a minor and a major approach, maybe the major approach won't have any maximum green time, but it does, right? But it does have a maximum green time because so then what do we do when there is no demand coming in from side streets? That's when the next one comes into play. It's the recall switch. Okay, so basically maximum green time will ensure that if this is the time that you want to, this is the time that you'll provide a phase, and then you'll switch over to the next phase, next movement, or next set of movements that you're providing to your signal. The next one is recall switch. Recall switch, each actuated phase has what we call a recall switch. Recall switch determines what happens to the signal when there is no demand, right? Almost all phases of a signal will have sort of a no recall, right? They will be set to no. The recall switch will be set to no, except for one phase, typically. That will be sort of so for example, if you talk about any of these signals here, like Broad and Bouchon Street, for example, right? So Broad Street, your main signal. So the recall switch on that would be keep the Broad Street on green, and rather than leave the Bouchon Street on red when there is no demand coming in from Bouchon Street, right? So that's the way you sort of, each actuated phase has a recall switch. The recall switch determines what happens to the signal when there is no competing demand, or when there is no demand. One recall switch is placed on position, all of the others are turned off. And yes.
So like the recall switch would be like, if there's no cars at the intersection, what it just sets the light to?
Yeah, exactly. Which will be set to green.
So it just sets like the major, just
the major, yeah, whatever you determine to be the major stream, you leave that green, and then everything else remains red at that time. In this case, when there is no demand present, the green returns to the phase with its recall switch on, right? Okay, if no recall switch is on position, then basically it remains where the last call was. Okay, if there is no recall switch on position, then it just remains. So for example, you might have two major intersections, right? So then all of the recall switch might be off position, and then wherever the last demand comes in, it remains green on that until there is a competing demand comes in from the other side. So that's and then if all recall switches are on and no demand exists, one phase continues to move to the next at the expiration of the minimum green. So again, you cycle. You typically don't want to do this. You don't leave all the recall switches on, because then you're sort of defeating the purpose of the actuation, right? So you just want to leave at least one of those approaches green. And then yellow and all red interval, again, safe transition from green to red. We talked about that. They are fixed times and not subject to variation. So for each movement, you will provide a yellow and green time, or yellow and all red time. Okay, so we'll provide that. How do we calculate that? We talked about some formulas. We're going to see those formulas again here. So we'll use those formulas to estimate our yellow and green times, or I'm sorry, yellow and all red time. So again, they are mostly safety features. So we'll always have them at a constant value. We don't vary the yellow and green time. I mean, yellow and all red time for each approach. We leave them as constant one. And then the pedestrian walk signal, and then there could be a bike signal as well. And I thought I would figure out There was some term related to bike signal that I still need to figure out. So I will look into that for sure. But the next one is the pedestrian walk signal, the walking man, and then the clearance signal for pedestrian is like, flashing hand, and then you have the don't walk, upraise hand. Which actuated signal, total length of green is not known. So this is kind of interesting. So whenever we are doing our sort of minimum green or maximum green and all those things, we always want to make sure that that's going to satisfy the corresponding sort of pedestrian requirement as well. Okay. Or if there is some kind of an LPI, leading pedestrian interval, that exists, so those also should be satisfied. Right. And then there are other types of controller that sort of lead to like all these different things. These volume density controller sort of add like more features to that, and those more features are basically related to providing variable minimum green, because area detector is capable of remembering the number of queued vehicles. So basically what they can do is like these volume density detectors or volume density controllers, they can see how much was your last queue and how much is that queue that you just sort of that had you had the queued ones. The minimum green time may be varied by looking at how many vehicles are queued, right? So if there is 5 vehicles that are queued, then you always provide that much minimum green time during that time of day, right? So you could look into that changing of the variable green time, not just based on one vehicle. Your minimum green time itself changes, not just the green time, but even the minimum green time could change. And then the gap reduction. Gap reduction is very, very similar to extension, but that extension time doesn't have to be the same, because these volume density controllers are not sampling sort of one point or one part of your approach. They are looking at the whole approach. So they can detect your queue length, they can look at how far back the queue goes and all of those things. And they could, and then, you could have sort of initial unit of extension, the final extension, time into green that gap reduction begins, and time into gap reduction ends. So basically this is, again, you're varying that gap. And again, you're just basically adding more complications if you have these types of features available. So for the purposes of this class, because obviously we don't have a lot of time to design all of these different types of detectors, for the purpose of this class, we're not going to focus too much on these volume density controllers. And we're just going to talk about these fixed minimum green times and fixed vehicle extension, because these are the things that you would actually code into. You could code into, the RBC controllers and vSim and things like that. So all of these things could be entered into vSim once you have all those numbers for a signal, and then you can model the operations of that. So we're just going to focus on that. Focus on the. So let's see. I want to talk about this. And let's see. And again, these are the gap reduction features. We're going to skip that. But now let's do this. Let's actually kind of go through this process of actuated signal timing and design. That's your sort of your homework problem pretty much, right? So that's what we're going to work on. In an actuated signal design, traffic engineer does not provide an exact signal timing. A phase plan is established. So what you're establishing is a phase plan, okay? And minima or maxima are set along with program rules to determine the green period between limiting values. So the first thing that you determine is what we call the minimum green time. Okay, this is the first thing we determine. And we determine that based on either the point or the passage detectors or the area of the presence detectors, right? So there is like, so there are two types of detectors, even within like, even if you have fixed minimum green time, even when you're dealing with sort of non-volume density controllers, you have two types of detection processes. One is point or passage detection, and this will be kind of like your loop detector that will probably going to have a 6 feet area. But then you could also have what we call the area or presence detector that looks at, a longer distance within the approach. Okay, even though it's not looking at the whole approach, it's not looking at the volume and density or anything like that, it's still able to look at sort of longer presence of the vehicles. So the difference being the point detectors only provide an indication that its call has been received. Okay, they don't know how many vehicles are queued up. They just know the call has been received, right? So this is like whether there is a vehicle on the detector or not, or a vehicle just past the detector or not. That's it. Okay. How many number of calls, experience, or service is not retained? If a point detector is located d feet from the stop line, it must be assumed that the queue of vehicle fully occupies the distance d. So basically, what you're assuming here is that if vehicle had the space available, so let's say you place the detector d feet away from the stop line, right? So I'm going to draw an approach. If this is your stop line, and your detector is located at a d distance away from the stop line, right? If you detect a vehicle here, let's say you detect a vehicle right here, you are assuming that this vehicle that you're detecting right here, right, is stopped here. That means all of this distance is occupied. Okay? So that's what you have to assume. This is what it means by that. When they say if a point detector is located d feet from the stop line, it must be assumed that a queue of vehicle fully occupy the distance d, where the distance d is from the stop line to the detector. How far is the detector? Now, again, as part of the your signal timing process, d itself may not be fixed. You can actually decide where you're going to place the detector. And again, if your detector is sort of, how should I put it? If your detector is a loop detector, maybe it's not that easy to shift. But then if a lot of your detection actually happens nowadays based on cameras, right? And those camera-based detectors, you could shift them. You can change your D rather easily because you can decide where camera's detection zone is going to be a little bit, you have some more flexibility there. So your G minimum should be long enough to clear a queue of vehicles, fully occupy the distance D. And this is what that G minimum looks like. G minimum is equal to L1 plus 2 times integer value of D over 20. Now, G minimum is minimum green time. That's what you're looking for. L1 is the startup loss time. Remember, that's the time once the light turns green, that time will be lost. So you need to basically provide for that. You have to have a provision for that. So that's why you're adding L1. And then you're basically assuming it takes 2 seconds to sort of, that's your sort of saturation headway you can think of. That's your 2 seconds to kind of discharge each vehicle. And then this INT is the integer function of D over 20. Now, given what's happening, so if you look at sort of the newish textbooks or new guidance that is available, sometimes you will see that this value is now being raised a little bit more because now our vehicle fleet consists of more SUVs, more longer, bigger vehicles. So sometimes you'll start to see that this value now is becoming larger. So that means your head-to-head spacing between vehicle and queue is becoming larger too, right? So that's so you will see this value being, 25. So don't be surprised if you look at your local guidance when you're practicing or whatever. If you see this value to be larger, that's a possibility. Okay, I'm okay either way in the test. Yes.
Caltrans uses 25.
Yeah, I'm not surprised that they use 25. Yeah, yeah. So that's fairly, so you start to see these things. Yeah, I'm not surprised if they use 25, which is certainly reasonable. Okay. So if you sort of do this type of and again, this is integer function, so that you always provide like an integer value plus the lost time. The integer function requires that a D over 20 is rounded to the next integer value. And again, a lot of times D over 20 and D over 25 will give you the same answer, by the way. Right? Because it's an integer function, sir, and you're supposed to round up. So, a lot of times they will come out to be the same, right? But, whatever you want to use is fine with me. but just keep that in mind. So that sort of gives you a minimum green time. Various agencies set L1 based on local policies, values between 2 to 4 seconds. And again, you might have different loss times for different phase. If it's a left turning vehicle phase, in the exam, you'll typically be given this value, and you could use, and then any reasonable assumption between 2 to 4 seconds would be fine. Okay? So that sort of establishes, if you have just a point detector, how much minimum green time you might want to provide. But if you have area or presence detectors, then this is another formula. You always want to provide that L1. But now your area or presence detector can essentially detect how many vehicles are in the queue. When area detectors are in use, the minimum green time can be variable based on the number of vehicles sensed in the queue when the green is initiated. So this is basically your, again, you're going to that, being able to provide that minimum green time based on number of vehicles in queue and number of vehicles stored in the detection area. So this N is, if you have 4, 5 vehicles in the detection area, then you could provide that level of minimum green time for that approach. Again, we can. So I think for the most part, I would be okay with focusing on the presence detectors because those are still fairly common. But if you want to, figure it out based on the queue length, you could figure out the N value. I mean, if you have the queue length available to you, if you can detect the number of vehicles lined up in the queue, you could provide that. The unit of vehicle extension services multiple purposes, as mentioned previously, right? The unit of vehicle extension. So now you want to determine how much would you increase your green time by if there is a continuous demand coming in. You figured out the minimum green time. Now you're figuring out how much additional time would you provide if that approach had more demand coming in. Okay. Now, again, this is the type of approach we typically do not use for pedestrians, right? We don't have pedestrians crossing or pushing the pedestrian button all the time. We don't say, okay, now we're going to extend the pedestrian interval like that. We always have sort of a fairly large pedestrian interval. We'll talk about that formula in just a second. But remember, this is only for the vehicular traffic here. Unit of vehicle extension serves 3 different purposes. We talked about that. The unit extension is selected with 2 criteria in mind. Okay, should be long enough that such that subsequent vehicle operating in dense traffic at a safe headway will be able to retain a green signal. Okay, obviously assuming maximum green is not reached, because once the maximum green is reached, you'll hit the yellow, right? You'll turn the signal yellow. But if the maximum green is not reached, the unit extension should be long enough such that a subsequent vehicle operating in reasonably dense environment at a safe headway will be able to retain a green signal. And then the next thing is the unit extension should not be so long that straggling vehicles may retain the green, or that excessive green time is added to green beyond what vehicle reasonably require, right? So basically, we only want to have accommodate one additional vehicle at one time. If there is another vehicle comes in, sure, we'll consider that. We'll add another green time. If another vehicle is right behind them, right? So we'll add 2 extensions. That's fine. But we don't want to have, one vehicle add so much time that's enough for passing 2, 3, 4, 5 vehicles, right? So that's the idea, is that we're trying to strike a balance. Now, if you kind of try to strike that balance, what happens is that very narrow range of feasible values will come out. Now, think about this. If you look at sort of the saturation headway is between 1.8 to 2 seconds, right? So we've talked about this, right? We've looked at different values. Even in ideal conditions, it could actually go higher, right? We've talked about, if you have left turn traffic or if you have upgrade, a lot of times this value could be even higher. It'll be impractical to lower the unit extension below these or even to these values. So our unit extension would always be somewhere more than 2 seconds, right? We obviously want to provide more than the saturation headway, right? Because if the continuous green vehicle require at least 2 seconds of gap between them. So always, whenever we are extending, we're going to extend by more than this value, right? So we always want to extend more than 2 seconds for sure. And the intent of an actuated signal is to maximize the efficiency of available green time. You don't want to provide an extension of more than 4 to 5 seconds, right? Because again, if you provide about 4 to 5 seconds, then you're defeating the purpose of kind of having that flexibility of changing your green times on all approaches. So the traffic detector handbook recommends a unit extension of 3 seconds to be used where approach speeds is equal to or less than 30 miles an hour, and 3.5 seconds at a higher approach speed, right? So that's really reasonable sort of criteria, right? Now, they talk about a little bit about volume density approaches. On volume density controllers with the gap reduction feature, the initial gap may be about half a second higher than those value. So you could start with a larger gap at the beginning, but then you keep reducing that gap because you have provided enough green to that approach, right? So maybe you can work with that. Again, we're not going to sort of worry too much about this for any of the problems that we deal with. But again, it's a reasonable way of kind of having some more additional flexibility. Now, but we've talked about, like, you want to have at least 3 seconds of detector time, and that's fine. But there is one thing, we mentioned that at the beginning, is that the unit extension must be or equal to or more than the passage time. Passage time is the time that it takes to traverse the distance between detector to the stop line. So our unit extension U must be more than passage time. D over 1.47 as 15 now. We're playing it a little bit more conservative. So even a slow-moving vehicle must be able to reach the stop sign or stop line from the detector. Even a slow-moving vehicle who's at the detector should be able to reach the stop line. A 15 percentile speed vehicle must be, and D is that distance between the detector and the stop line. Okay. Now this S15, see this 1.47, we've talked about this. 1.47 is nothing but 50 to 80 divided by 3600. So now the good news is that you can plug in S15 in miles per hour, and you can plug in distance D in feet, and you'll be fine. And you'll get your answer in seconds. Okay, so that's what this 1.47 is for. Again, units, remember these units. Now think about, because as I told you, right, detector location by itself is also not fixed. You can determine where you want to place the detector. So one of the things about, placing the detector is that you never want to place your detector where a vehicle could go undetected, right? So what does that mean? Why would vehicle go, if you're placing it on an approach, why would a vehicle remain undetected? Think about your intersection of Santa Rosa and Foothill. Think about that Chevron gas station driveway, right? If there is detector placed far enough ahead, or at least maybe it's because I think they use camera-based detection. But let's say if your camera doesn't capture vehicles that are so close to the stop line, you might sometimes miss the vehicles that might come out of the Chevron driveway and want to go through on that intersection. So come out of the Chevron driveway and want to go through, and quickly, I don't know if you're imagining this clearly, but if you look at maps.google.com, let's take a look at, this is the intersection approach. And let's do the layer. Yeah. So if you're this is the Chevron gas station. If you're not providing detection on this part of the roadway, then you might be missing out on who's coming out of this approach. And so you must be able to capture that with your detection. And again, there might be driveways that are even closer sometimes. It's not advisable, but sometimes does happen. Yes.
That's like, I guess, the case of them. Are we talking about for like the unit or vehicle extension?
Any type of detector, you want to make sure that, let's say if you're capturing the area, no part of your queue is sort of getting undetected. So sometimes, the camera might have, where you're detecting vehicles might have a certain range also. So you just want to be careful that, whatever your detection range is, it's capturing all the vehicles that might pass by.
So it's like vehicles turning, I guess, right onto the highway.
They won't need the detection.
It's going to be higher than the unit extension.
Right. And then, you typically don't provide extension for the right turn because, we do allow right turn on red, right? So you don't necessarily worry about them having to have a green, right? So our focus would be the approaches that cannot move on red, right? So they cannot move at all on red. So that's, and again, this might become important question if we ever go to a situation where now we're saying we're not going to allow right turn on red, right? Because in right turn on red, the problem is, as a right turning vehicle, your focus is a lot on, if this signal is red, presumably this might be green, and you're focused on sort of maybe a vehicle approaching to the left here, and you just have to be careful about pedestrians and that, because that could cause some problems. But again, because we are allowing right turn on red on this approach, more often than not, you won't have to worry about kind of providing any kind of right turn phasing, right? Because you're allowing that movement to go on red. So you don't have to worry about detection and all of that on the right turn approaches for the most part. Okay, so let's go back to, let's go back to detector location. So definitely we don't want to miss anything, right? A practical minimum limit on minimum green time is the assumed startup loss time 2 seconds, right? So we want to L1 plus 2 seconds, right? Because this is the amount of needed to process a single vehicle, ranges between 4 to 6 seconds, depending upon what your loss time might be. So if you're using the strategy of L1 plus 2 seconds, right? If that's what you're using, that's a reasonable strategy to provide how much minimum green time you want. I mean, where you want to place your detector. If this is the minimum, so a good strategy is to figure out, okay, what's the minimum green time I want to provide, and then make sure that you figure out the D based off of that. So L1 plus 2 seconds. So they have a quick question here. A minimum green time on approach. Actuated signal is set to be 6 seconds. So if you want to provide a minimum green time of 6 seconds, where you want to place the detector, right? And loss time is assumed to be 4 seconds. So 6 equal to 4 plus 2 integer D over 20. You get D over 20 is equal to 1, right? That gives you any value between 0.1 feet to 20 feet. And again, if you use 25 feet here, then it gives you any value between right at the stop line all the way back to 25 feet, give you the same, you will still be able to meet your minimum green time requirement of 6 seconds. Is everybody clear on why our answer is going to be 0.1 to 20 feet? Because our function is integer times D over 20. Okay. An integer function basically rounds up the answer to the next integer. Okay. So any 0.1 rounds to 1. 0.2 rounds to 1. 0.8 rounds to 1. Everything just rounds up to 1. Okay. Again, if this was 25, your answer here would be anywhere between 0.1 to 25 feet from the stop line, you can place the detector. There is other strategies, is to equalize unit extension and passage time, right? So that's another way of, making sure that you are, because you want the unit extension to be more than or equal to P. That's another strategy. Second strategy is place the detector to equalize the unit extension or passing time. And an approach with an actuated signal, a detector is placed such that unit extension of 3.5 seconds is equal to passing time. So you could solve for D, this equation, right? So if 3.5 seconds equal to D over 1.47 times 40. So 15th percentile speed is 40. So you could solve for that. So you could place the detector at 205.8 feet. Now, why might we want to do that? What's the purpose of being able to do this? Right? The advantage of such a setback is the vehicle arrival when there is no demand present when the signal is red. So now the good news for this is that you can actually turn your signal green, and this we use it in a lot of places actually. And you might have seen in certain approaches, if you're approaching them in nighttime, right? What happens? You are still approaching the signal, the light starts to turn, on the conflicting approach, the light starts to turn yellow. Because they are now starting to give you the green time, even though you haven't fully approached, because the detector is placed so far back right, is that now you're detected, and the signal controller already starts to make arrangements for you to get the green by the time you actually reach the stop line. Okay, so the advantage of, like, if you provide, so this is, you can see that this is providing, if you look at the answers that you got, this, if you use this approach, you're getting the approach detected 206 feet away, right? This is the advantage, right? But the disadvantage is, you might miss vehicles too, right? If you're, the approach that you're talking about, if you're detected so far back and you have some kind of a, driveway that feeds traffic to your signalized intersection approach, then you might miss out. So the advantage obviously is that vehicle would not have to stop at all or wait for the green. Yes.
Would the best of both worlds be to essentially put a detector at 20 feet and then put another one at 15?
Yeah, so that's basically what these presence detectors are, not presence, but the area detector allow you to do, right? So you're sort of allowing for a longer area to be present. The other thing is that one thing is that if you provide the detector at 206 feet, the other disadvantage is this right here, because your G minimum formula depends on where your detector is. Boy, look at this. 4 plus 2 times integer of 205.8 divided by 20. 26 seconds of minimum green time. That's kind of a lot. Really, really high green time, right? So that will be excessive green time, because the competing vehicle will be forced to wait for 26 seconds at a minimum. That's kind of bad, right? But, so that's what you were saying before, right? So what you were saying is exactly right. For this reason, longer setbacks in which unit extent and passage time are equal are used only where presence or area detectors are in place, where you can detect a larger area rather than just in small a detection based. So these detection based detectors are only kind of looking at 6 feet. They're 6 feet by 6 feet in length. So they only detect the presence of a vehicle in the 6 feet area. But the area and presence detectors are way longer. Okay. And we already talked about this. The detectors must be placed such that no vehicle can arrive at the stop line without having to cross a detector. So in many urban and suburban settings, this required detector to be placed quite close to the stop line because there is driveways all over the place, right? So that's what that means. Area detectors are more flexible. They can detect vehicle entering the detection area from any side. That it is the only location on the front of the area detector that is limited, as described previously. Okay, so now once you figured out where you're going to place the detector, you figured out your minimum green time. The next thing you do is figure out your yellow and all red interval, which is these formulas. We've seen these formulas before. Now, one thing to note here, and you might want to make a careful note in your notes too, is weirdly, they use the value of L, right? The capital L. This textbook, I think that's a problem with this book a little bit, and you want to make sure that you pay attention. The L here in this equation 20.5, this L is representing the length of the vehicle. So this L here in 20.5 is vehicle length. Okay, the capital L is vehicle length. And we've seen these formulas in our notes before. So you could use it, you can derive and it's basically just figuring out how much time you need to clear the intersection, how much all red time you need to kind of clear the intersection, all that good stuff. Now, they also use this L, right in equation 20.6, this capital L here, in 20.6, L is lost time per cycle, the total lost time per cycle. Okay, so just kind of be careful when you're using this. 20.5, it's detecting the vehicle length. They couldn't use small l because I think there was small l. They used it before as well on something else. The L1 and L2 are like startup lost time and clearance lost time. So there is a lot going on. Just make sure that you're paying attention to those as you're applying those formulas And these formulas make sense, right? The all red would be based on how much length you need to clear out the intersection and all of that. So let's look at this. So these formulas are fairly, and again, yellow and all red must be known to determine the total lost time. Total lost time is typically, L1I plus L2I, startup and lost time. L2I is typically capital YI minus EI. So yellow interval minus the startup lost time, where capital YI is the yellow time and the all red time for that phase. Okay. So yellow and all red time also help you determine approximately, give or take, what are going to be your lost times. Okay. So if you use default values of L and E, L1 and E, L1 is your startup lost time, and E is your not your clearance loss time, but it's the encroachment time, the part of the all red vehicle, which aggressive vehicle, part of the all red time that aggressive vehicles keep using to clear the intersection, right? So E is the encroachment of effective green into yellow and all red phases. And again, if you use these default values, because L1I, the default value is 2 seconds, and for EI also the default value is 2 seconds. So if you use these default values, let me clear out these. When default values of L1 and E are used, the total lost time per cycle is equal to the sum of yellow and all red phases associated with the critical movements in the cycle. Okay. So typically, once you figure out yellow and all red interval, you would have figured out your total lost time as well, because you can assume default values, and then that's how you end up with this. Huh? So being able to estimate yellow and all red is pretty important, because that also determines your lost time per cycle. Okay. And then the critical cycle, then you figure out, okay, what is my maximum green time in the critical cycle? And again, remember, this is the exact formula that we saw before. It's the formula for the desirable cycle length. C-des, we did the desirable cycle length formula. It's exactly the same formula. The couple of things that we talk about here is that for V by C ratio, we'll use pretty high values for V by C ratio. Okay? Because again, with the actuated signals, you have that flexibility. So you could get pretty close to the volume to capacity ratio. You don't have to use a volume to capacity ratio of 90%. You could be 0.95 or higher. Okay, so you could operate your signal as close to capacity as possible. So you will see that they note that here. It's 0.95 or higher in most applications. Okay, so CI would be this one. Lost time, this is the total lost time per cycle. Capital L, again, in 20.7, L is the lost time per cycle. Remember, it's not vehicle length, right? So 20.7, again, might be worth noting. In 20.7, L is lost time, the total lost time per cycle. Got it? And then you can start allocating different green times to it. Green line for one approach, C minus L over VCI over VC. VCI is your critical lane approach for that phase. VC is the total sum of critical lane volumes. And then, you get your effective green time, capital C minus lost time, and then you determine the green time in that ratio. Okay, so you'll get your effective green time. Right, so you got this. And then once you have that, you're basically pretty much done with that, allocating the green time for that approach. So you have the minimum green time, and then with this, you can determine the maximum green time as well. Okay. Now, the thing here, though, is the difference between semi-actuated and fully actuated signals. So we'll talk about that in just a second. Your total cycle length will be GI plus YI. Okay. the actual maximum green for actuated phase. Okay, we'll talk about this in a second. 20.9, we'll come back to it in a minute here. But before that, I want to talk about pedestrian requirement for actuated signals as well. The pedestrian required the following time to safely cross a street. Pedestrian green phase will be minimum pedestrian green time, GP, at least 3.2 seconds. Then a length of the crosswalk over ST. Walking speed for pedestrians, default is 4 feet per second. You could use lower values if you wanted to increase the time. And NPEDs, number of pedestrian detected, in one crosswalk per cycle. This number could be based on historical data, NPEDs, or if you have some kind of a video camera detection, you can, do it phase by phase as well. Okay. So NPEDs is the average number of pedestrians crossing the street. And then you add some more time. You don't add a full second for each pedestrian because obviously pedestrians will walk in some kind of a group. And then, you'll have some kind of a crosswalk as well. So what you want to make sure, all pedestrians are permitted to be in the pedestrians are permitted to be in the crosswalk during the vehicle green time, plus the yellow and all red intervals. So safe operation will happen when you have GP, pedestrian time less than or equal to G plus Y. Okay. So GP should be less than or equal to G plus Y for any given phase. Right. So the pedestrian crossing and the parallel vehicular movement, this requirement for this G plus Y comes from the vehicular movement. GP comes from this formula. GP must be less than or equal to G plus Y. Okay. Because remember, after this G plus Y, the other side has to turn green, right? And then you don't want pedestrians to get caught up in that crosswalk when the conflicting through movement starts, right? So this idea, this is what I'm going to look for here. So let's say if I have a signal approach, this is my crosswalk right here, right? So I'm allowing this green to go. So the G plus Y plus for this. Okay, so this formula and GP for this. So GP is measured for this approach. G plus Y is for this approach. GP should be less than or equal to G plus Y. Why? Because if I have exhausted this time, what would happen? I will be moving this set of vehicles, right? And then from this set of vehicles as well, maybe, right? Depending upon how the phases are set up. If that happens, you don't want these to be pedestrians to be here, right? So that, and again, if there is some kind of a leading pedestrian interval, that helps, right? So you could have that, you could provide that for additional sort of clearance. Now, there are some, the value of NPEDs varies, the cycle length is variable. Minimum, this results in a maximum feasible number of pedestrians that might cross in the signal cycle. Green time varies cycle to cycle. Safety can be only assumed when if your G minimum meets that requirement. Remember, our cycle length will change. Our minimum green time will change. I mean, our actual green times will change every cycle. So this requirement that I showed you here has to be met for minimum green time for each cycle. Okay, this is very important too, right? Because whatever green you're providing, when pre-time signal, when safe crossing is not issued, cycle's length must be increased. With actuated signal, though, safe crossing based on minimum green is most often not provided, right? With actuated signal, what we do is, now this is something, increasing minimum greens to actuate all the time. You don't want to do that every cycle. You don't want a minimum green time to be increased all the time, right? So what we do is, if you cannot do this, if your minimum green time does not always provide for pedestrians, you have a couple of options here. You must provide the pedestrian push button. So that's kind of what you could think about. What happens in downtown, you might have noticed on certain signals in downtown, there is push buttons, but on certain signals there is not, right? And what's the purpose of this? The purpose is that, on a lot of signal approaches, the minimum green time for vehicular phases is sufficient for pedestrians to cross that corresponding phase. Then you don't provide the push button. But if that's not the case, you only extend the minimum green time when pedestrians are present and push that press button. And our newer, sort of more pedestrian-friendly design guideline are telling us, hey, we should always provide. We shouldn't have to have a pedestrian push button. We should always have enough green time for pedestrians to be able to cross, right? So that sort of is, or maybe if we have a pedestrian phase alone, like a fully pedestrianized phase, should be available. Again, there is arguments to be had on both sides. Because obviously, if you're talking like late at night when the deliveries are happening, you're not going to have, pedestrians in there, right? So late night when all the shops are closed, only thing that's going on is deliveries. So then, the things could change. So I think this is a reasonable compromise. Pedestrian signal rest and don't walk indication. When the push button is actuated, then that's when the next green phase, the minimum green time is increased to this value to accommodate the pedestrians. Okay. When the pedestrian minimum green time is called for, the walk signal is for 3.2 plus 0.27 NPEDs, and your flashing yellow arrow is there over L over SP time. So this time, the L over SP, again, they use another different L here. Okay, L is the length of crosswalk now. So they use 3 different values that they denote with capital L. So I want to make sure that you note that in 2010, L is just make sure that you pay attention to that. Okay. So, I think what we should do probably is just kind of do an example here. Okay. So one thing I want to note in the example that you could potentially do or work out is, let's take a look at. So this is the example, very similar to your homework problem, I think, right? So you're talking about a semi-actuated signal. Okay. And they talk about different things, and it's fairly similar to whatever is given here. I think you could follow along the example. I want to focus on a couple of things here. Let's first think about what is the sum of critical lane volumes here. What is the sum of critical lane volumes is what I want to focus on first. First, note that, this is just a simple 2-phase signal. No, actually, they have a left turn demand. See. Semi-actuated, already converted into 3, in through vehicle units. So all these are based on through vehicle units. Sum of critical lane volumes. And then let's see, I want to see something here. It's a 2-phase, right? Yeah, it's a basically what they're saying is that this is a simple 2-phase signal where you have sort of eastbound, westbound going at one time and northbound, southbound going at the other time, right? And how are you going to design the signal? And again, this is all converted into through vehicle movement. Yes.
If it's, I guess, not converted to different movements, we have to do like that E for left turn, E for
right. And then you will need obviously some more information.
The critical lane.
Yeah, critical lane volume is going to be also, you'll have to divide. And then the other thing is that here, the other thing that you have to think about is that, the 600 TVUs is a mix of left and through, right? You couldn't combine them if you had a protected left turn phase, for example, because then that will be a separate phase, and then you'll have to devote critical length to that phase. Okay, so just kind of be careful here. Is that if there is a third phase for the left turn that's exclusive, then that have to be accounted for somehow. So something, this is a kind of an important thing. So southbound movement has higher volume, and then both have one lane. So you basically say, okay, I'm just gonna have that. So, you could see that in the intersection, I have one lane. Here I have given 2 lanes here. So I have total 1600. I should be able to divide that into 2 lanes. So 800 from here. So which one would be critical volume? The eastbound or westbound? Again, assuming the north is up. Which one is my critical lane volume in the east-west direction? 800, right? 1601, but it's divided in 2 lanes. So I need to accommodate 800 through vehicle units on that east-west phase. How much do I need to accommodate on the north-south phase? 240, right? Because that's the higher number. So my sum of critical lane volumes that I need to account for is 1040 TVUs per hour. Okay. And I could use that 1040 TVUs per hour in this formula if I knew the loss time. If I knew the loss time, and my loss time is going to be the sum of yellow and all red interval for each cycle. Yellow and all red interval for each cycle. Remember we said default values of use for 2 seconds is used for both L1 and E. The loss time per cycle is equal to the sum of yellow and all red times in the cycle. So if you apply your yellow and all red interval for each approach, let's delete this. You will be able to come up with 3.2 plus 4.3 plus 2.3 plus 1.0. You add those up, that will be your loss time. Fairly reasonable assumptions there. So just add up all the yellow and all red time, becomes your total loss time per cycle. You could use this then to figure out critical cycle length using the desirable cycle length formula that we talked about. Again, V by C ratio that you're using, it's going to be 0.95 or higher. PHF was given. I think they even gave you the V by C target to be 0.95. Don't be surprised if that value is higher when you're doing the actuated design. Then 41.1 second. Now, there are other thing about cycle length in actuated design. We don't round it up to next 5. We always, just leave it whatever it is. Okay. So 41.1 second. How much time are you going to give to each approach? This is that formula. G1. So this G1 represents the green time for north-south. G1 represents green time north-south. North-south. And then G2 represents for east-west. Right? So you can compute these G1 and G2 because, see, you're providing a 41.1 cycle length. You're providing a 41.1 second cycle length. Out of that, 10.8 is getting lost. You can't use it. Right? And then you apply a ratio of whatever the critical lane volume for that approach divided by the sum of critical lane volume 1040. Okay? So you're providing a 7 seconds of green time on the north-south approach. And then on the east-west approach, you're providing 23.3 seconds. So that should be your allocation. Now remember, here is again another rule of thumb comes in. But this is very important to remember. Is because it's a semi-actuated signal, this is not a typo. This is not a typo. It won't give you both green time to be max. It won't give you max green time for both approaches in a semi-actuated signal. In a fully actuated signal, when you're solving a fully actuated signal problem, the value that come out of this rule of thumb, and I'll talk about this rule of thumb in a second here, give you max, if in a semi-actuated, it gives you max time for the minor street and minimum time for the major street. Okay. So this is, I want to say here, max time for the minor approach. And then this gives you minimum time for the major approach. Does that make sense? So make sure that you note that. Okay? So when you get these G1 and G2 values based on your detectors or whatever, and then they say effective green time and actual green times are equal because, again, you're using the same default values for. So that's why you can convert G1 and capital G1 are the same because, because you're using the default values for L1 and E. This is what happens. The standard practice establishes maximum green time for the minor and minimum green time for the major by multiplying those green times by 1.5. Okay. Now here, again, this 1.5 factor is not etched in stone or anything like that. Different agencies have different guidance, different ways of doing signal timing. I wouldn't be surprised if you see 1.7. You see a little bit less than that. That's fine. Just providing some additional green time for each cycle. So let's see. Now, one thing that you want to make sure is that when you do G max of 10.5 seconds, right? The G max is the maximum green time you want to provide on the minor speed. So max time for the minor approach. Remember we said that? You want to make sure that whatever max you're getting here, whatever max green time you're getting here, compares favorably to the minimum green time that you would have gotten at the very beginning for each approach. Okay? So you would have applied these formulas, because remember I showed you minimum green time is the most important thing to get, or at least the first step to get. You want to make sure that this minimum green time is accounted for. Now, you might think, why would minimum time ever be more than maximum time? It could happen, yes.
So then you don't get like a really, because if it's a really short, low G1, then you might have it less than you.
Yeah, and actually they talk about a next example here. So if you look at this next example, there, it's kind of like a variation on example 2.1. What would change if the side state critical demand volume was only 85 vehicles per hour rather than 240 vehicles per hour, right? So now your side state have very, very low demand, right? Really low demand. That if you solve it, your G1 comes out to be only 1.7 seconds. If you repeat the steps and everything, your G1 is actually, it's going to come out to be 85 divided by 885, it's 1.7 seconds. And that's going to be a problem, right? Because now this 1.7 seconds is, and even if you multiply that by 1.5, I think they did that. Yeah, so it comes out to be like 2.6 seconds. 2.6 seconds. That's a problem because 2.6 seconds is actually more than, I mean, less than the minimum green time you want to provide. So your max green for minor approach, max time for minor approach is 2.6 seconds, which is not even enough to meet the minimum green time requirement. So what you'll need to do is, you need to set this up a little bit, okay? You have to sort of come up with another way of kind of maximizing the green time. So minimum green time accommodates one vehicle. So maybe you say, okay, I'm going to at least accommodate 2 extensions. So you come up with like a 10 seconds of green time window. So that's one thing to remember, is that sometimes this could happen and you have to make sure that you track it. In the first example, that did not happen. So that's kind of what I'm going to continue to discuss. And then pedestrian crossing requirement, pedestrian cross the minor street during phase 2. Crossing requirement must be compared to the minimum green time plus yellow already provided for phase 2. Number of feds is per cycle. So your number of feds per hour is 25. Your critical cycle length is 56.3 seconds that they calculated. So you got the number of feds per cycle. You came up with GP2 for phase 2. You came up with 10.8 seconds. The 10.8 seconds must be less than G minimum 2 plus capital Y2. That's the yellow interval and all red interval for that period, for that phase. The 35 was probably the minimum green time that we established right here for the major approach. So usually this would be fine, right? Because major time, when you're crossing the major street, that should be okay because you have 35 seconds of green plus 4.3 seconds of yellow, 1 second of all red. You got 40.3 seconds. Your pedestrians only need 10.8 seconds. The minimum green time provides more than enough time for safe crossing. So no push button is needed also. Pet signals are optional, but I think it's a good idea to provide it always. Okay. Now you have to look at the other phase too, though. This is usually the problematic part. When the pedestrians have to cross the larger distance. When they're crossing the major street, this is the problem, right? When they're crossing the major street, right, they have to go longer distance, but the vehicle requirement on the minor street is going to be pretty small. So that's where the problems come in, right? Because your minimum green time is 4 seconds, and yellow and all red you added 9.5 seconds. But if you calculate your pedestrian crossing interval, it came out to be 15.3 seconds. Okay. What does that tell you? Can you accommodate the 15.3 seconds with your 9.5 seconds of green time? No, right? So they're not accommodated. So they're not safely accommodated. Pedestrians crossing the major street, a pedestrian push button must be provided and pedestrian signals must be mandatory. Okay, whenever there is a pedestrian detection, the next phase will provide a minimum green time of 15.3 seconds. And then regime in 1 for pedestrian will be pedestrian green time minus yellow minus all red for that approach, 9.8 seconds. And then you could calculate the. So for that approach, whenever there are pedestrians, you'll provide that detection and then go from there. Okay. Now, what changes when this is the same problem, but now we talked about this a little bit, so you could review that. Should be able to understand. They explain it fairly well here. But one thing I want to talk about a little bit more is this actuated signal, fully actuated approach. What's the big difference between the two approaches? Fairly reasonable. You got 650, 110, 400, 300. And again, they already give you the lane configuration, so you're fine. They give you 2 lanes, so your left turn. And then this is, again, a rule of thumb is, if your left turn volume is more than 300, yeah, you probably need 2 lanes. If it's less than 200, you can work with 1. Between 2 and 300, it's a little bit up to you. So there's some flexibility there. But again, they give you the lane configuration. So you know that this left turn volume is divided into 2 lanes. So if I'm gonna ask you to time a full signal, I'm not gonna also ask you to determine the lane configuration as well. I'll probably ask you in a separate problem, and then do that work, and then in a separate problem. So if I'm giving you the lane configuration, you got 2 lanes for left lane, and then you got 1 lane, 2 lane, 3 lane to accommodate the 4 lanes to accommodate the 1600. Okay, and then 700 divided into 2 lanes. So yeah, let's quickly figure out. So you could actually figure out what's your critical lane volume is, right? I think they do that here. They do that right here, and then divide by appropriate. Left turn is 400 divided by 2 lanes. 1600 divided by 4 lanes. Monroe is left turn divided by 1 lane. Monroe through right is 350 divided into 2 lanes. So you can come up with their critical lane volumes. So all of the calculations are fairly similar, and you could use your yellow and all red time as your default for lost time. But here is the rub. When you have a fully actuated signal, here we have a 4-phase signal. All 4 phases are computing that. These times, for major, for minor, for whatever, all of these are maxed. All of these are maximum green time that you get. Remember, this is a big difference. Here, all of them are max time. Here, okay? So just remember that. When we were doing semi-actuated, we got minimum green time for the major approach. We got the maximum green time for the minor approach. Okay. But when you have fully actuated signal, all you get is the maximum green time. And again, you can then figure out the cycle length. You can make sure that, so in this example, there were no pedestrians, but if there were pedestrians, you'll make sure that, your minimum green times accommodate pedestrians. Otherwise, you'll provide a push button, right? All of that thing. So that's your, this is the big difference. Here, you get 4 max green times, 3 max 1, max 2, max 3, max 4. You have 4 phases total. And then because you have 4 phases, look at the loss time. Fairly high loss time here too. Okay? So remember that piece. Let's see. Is there anything else that we want to talk about? Yeah, I think this is fine. I think there is one more thing that I wanted to mention here. Second. So in the problems, they will say, so in some cases, some jurisdictions, it says as pedestrians are permitted to be in the crosswalk during vehicular green time plus yellow and all red, then you do G plus capital Y. But there might be jurisdictions that do not allow pedestrians to be in the crosswalk during the yellow and all red interval. Then your GP must be less than or equal to G in that scenario. Does that make sense? Right? If your pedestrians are not allowed, so if this situation was reversed, you'll take out this Y from this equation. If pedestrians were not allowed. All right. So what I'm going to do is I'm going to stop here. And with this now, you should be able to time the signal that's in your homework problem. Again, always open to reasonable assumptions. In the test, I will make sure that you know exactly what you should be applying. But in the homework, there would be problems that require you to maybe interpret some things one way or the other. So be prepared to do that. I'm happy to confirm that with you. Make sure that you remember the office hours, extra office hours. I know I do have office hours tomorrow, 12 to 2, which I don't want to change because a lot of other classes students utilize that. But I will have, before the homeworks are due, I will have these office hours, 11:30 to 1 this week. So feel free to stop by. Yes. Yeah, so next text is 1 week from today. Yeah, sorry. No, I did not announce it today. I put it in the syllabus for this Thursday, but then because we are 1 week behind or 5 days behind our schedule because we had a couple of guest speakers. So it's moved by 5 days. Okay, so our next test is Tuesday of the following week, 1 week from today. Again, very similar to the homework problems, but again, less ambiguity. But in the homework problem, expect ambiguity. Okay, so look into that. And you have the handout. And again, you have this whole textbook there too. But remember, for the textbook, do not worry about the highway capacity manual because those keep changing. This is very old information. And signal timing, they have fairly reasonable information. But again, don't be surprised if your jurisdiction has some slightly different ways of doing things. Okay. All right. So I'm going to stop here. I will see you on Thursday. Thank you.
Yeah.